Assalamualaikum and hi. We are from Group 7 would like to present a group project about the production of nitric acid. Our group consists of 4 members namely first, Sibasini, Yong Jili, Zain Nazarif and Muhammad Fikri. Firstly, introduction. Nitric acid is a colorless, corrosive and toxic mineral acid that turns yellow over time due to the accumulation of nitric oxides. It is widely used in the manufacture of fertilizer, dyes, explosive and the polymer industry. Exposure to nitric acid can cause immediate irritation of the respiratory tract, pain and the dyspnea in humans and animals. Let, let we see about the history in industrial production of nitric acid. About 80% of nitric acid production is dedicated to the fertilizer industry. The history of nitric acid produce include key development. 17th century, Johann Rudolf Glauber produced nitric acid by distilling potassium nitrate with sulfuric acid. 18th century, Antoine Lavoisier, building on Joseph Priestley works, show nitric acid could be converted from nitric oxide and air. Henry Cavendish determined its composition in 17 polymer. 19th century, Humphrey Davy used electrolysis to produce nitric acid from dissolved nitrogen gas in 1806. 20th century, industrial production began in 1905 with the Berkeley Eye process. Later, the Oswald process after the Haber process made ammonia production efficient in the world. Albert Norden also developed the method using electrolysis of calcium nitrate in 1913. Next, we go to the report. In this report, production are designed to produce 280 tons per day, where 60% of that is a nitric acid that we can produce. The process include block flow diagram (BFD) and process flow diagram (PFD). We also explain the process description of each process involved, among which the component we will explain such as compressor, reactor, heat exchanger, stripper and other than that. With a detailed parameter and description.
Okay, so next one I will explain about the block flow diagram (BFD) for our plant. So the block flow diagram consists of some processes such as compressor, vaporizer, reactor, heat exchanger, absorption tower and bleacher. So first one, at the bottom, clean air will insert by compressor and then through air filter to filter some dust. And then the top one is ammonia vaporizer and ammonia superheater. Then both will enter the reactor to process some reaction. Then through waste heat boiler, condenser, oxidation and the absorber, the water will insert to cool down, and lastly bleacher. So the HNO3 will produce. So next one I will explain about our BFD process flow diagram that is more detailed compared to BFD. So the first one, at the bottom the clean air will insert to air compressor and then go through the air filter, then insert back to centrifugal compressor. So at the top the ammonia will insert to ammonia vaporizer and then go through ammonia splitter, then it goes to reactor. So it will process, then the product will go to the basic boiler, then condenser to cool down the gases, and then it will enter the oxidation unit. After that we will enter absorption tower. At the absorption tower the water will insert through at the top of the tower, and then lastly it will go to bleacher, then the product of HNO3 will produce. So next one I will explain about detail about the instrument symbol. So the first one is axial compressor. The first stage involves low pressure compression from atmospheric pressure using an axial compressor driven by turbine. So this is will the clean air will enter. Then it goes to air filter. Industrial air filter removes solid particulates and molecular contaminants to improve air quality. They consist of a study frame filled with a filter media sealed to prevent leaks. Okay, so next one is centrifugal compressor. This is after the air enter the air filter, it will go through this centrifugal compressor used to pump various fluids including corrosive liquids and suspensions by using centrifugal force. This pump adjusts gas flow pressure for processing, enable gas flow through reactors, heat exchangers and pipes, and refrigerate gas flows for cooling and liquefaction. So the next one about the ammonia vaporizer. A shell and tube heat exchanger with two passes per shell and internal baffles. It produces a continuous stream of ammonia vapor using hot water, electric steam or steam, regulated by a flow control valve. So next one, ammonia superheater. The shell and tube type heat exchange of similar mechanical construction to the ammonia vaporizer. Next one is the reactor. The vessel must ensure even passage of feed gas over the platinum or radium catalyst gauge. A random pack flow distributor is suitable. Reacting mesh catalyst and filter gauge 25 sheet each, total 24 kg are fixed by lateral support across the reactor. So this is where the process of clean air and the ammoniacal process will occur. So next one is passive boiler, WHB. The shell and tube type heat exchange heat pressurized 400 kilopascal hot water from 170 Celsius to 250 Celsius vapor. Tube side design pressure is 5000 kilopascal and waste heat boiler cools reaction gases from 595 Celsius to 280 Celsius. Next one in condenser. This heat exchange condense weak nitric acid from 185 Celsius to 60 Celsius using the ionized water as the cooling medium. Lastly, the three main process unit are oxidation unit, absorption tower and bleaching column. The oxidation unit is an empty pressure vessel that mixes input gases with additional air from the bleaching column, increasing oxygen levels for further oxidation and raising the temperature to 140 Celsius. Next is the absorption tower. The absorber is a sieve tray type column with a bursting disc for pressure relief. Each tray has cooling coils for the absorption liquid with two separate cooling circuits using the ionized water. So the water will enter at the top of the tower. Okay, so lastly the bleaching column. The bleaching column is a small sieve tray column where impure acid descends from the top tray while air is bubbled up through the liquid. To remove dissolved nitrogen oxide, the acid collected at the bottom is the desired 60% weight product of NaSO3.
So I'm going to explain process description. First is compression of clean air. Ambient air is drawn into a compressor where it is compressed to a pressure of 800 to 1000 kPa and heated to about 150 to 2000 degrees Celsius due to the compression process. Second is air filtration. Compresses air passes an air filter to remove any impurities or particulates before entering the reactor. Next, we go through to the ammonia vaporization and superheating. Liquid ammonia is first vaporized at around negative 33 degrees Celsius and then superheated to approximately 120 to 150 degrees Celsius. To ensure it is fully in the gaseous state. In the reaction of ammonia oxidation, the compressed air and superheated ammonia are fed into a catalytic reactor containing a platinum-rhodium gas catalyst. At a high temperature of 850 to 950 degrees Celsius and a pressure of 800 to 1000 kPa, ammonia reacts with oxygen to form nitrogen monoxide and water vapor according to the reaction below. Next, in the heat exchange process, Hot gases from the reactor are cooled to 200 until 300 degrees Celsius in a heat exchanger. Recovering heat used to preheat incoming air or ammonia, improving overall process efficiency. While in the absorption process, cold gases enter an absorption tower where nitrogen monoxide is oxidized to nitrogen dioxide, which then react with water to form nitric acid. The process occurs at 50 to 80 degrees Celsius and 800 to 1000 kPa pressure. This nitrogen dioxide is adsorbed in water to form nitric acid through the reaction below. So next, we go through to the stripping process. The nitric acid solution is sent to a stripping column to remove dissolved nitrogen oxides, crucial for ensuring the purity of the final product. Stripping occurs at 50 to 70 degrees Celsius and slightly lower pressure than the absorption tower. And the last process is storage. The purified 60% of nitric acid is stored in a specially designed tanks capable of handling its corrosive nature. This tank can store up to 560 tons, enough for 1 until 2 days of production.
Last but not least, conclusion. In conclusion, nitric acid is a critical component in Malaysia fertilizer and industrial sector, with 80% of production dedicated to fertilizer. The production process involves multiple interconnected units, each serving specific function to produce pure nitric acid suitable for the various industries.